Good morning, my name is Maria Buritica, and today I'm presenting the cellular response to nitrogen mustard on sensory pain in mouse keratinocytes Pam212 cells. To start, nitrogen mustard is a referred chemical that can produce skin inflammation, skin fibrosis, and blistering. It was also used during World War I and World War II. For this project, we used cannabinoid receptor and opioid receptor, which are G-coupled proteins involving appetite, emotions, inflammation, and pain. As shown in figure 1, the pain pathway starts with the stimulus that can be on the skin, and then the cannabinoid receptor is activated to bring the signal to the neurons, where the nociceptors activate a pain inhibitor that go back to where the stimulus is located. For my review of literature, Bidlack in 2006 found that opioid receptors are involved in the immunological responses to pain. Then, Brax in 2008 showed that cannabinoid 2 receptor is involved in the regulation of central immune responses that can lead to pain. And finally, Fator in 2011 showed that cannabinoid receptors and opioid receptors have a crosstalk in drug addiction and relapse, which is an error in abstinent rats. This led to my hypothesis, which is that exposure to nitrogen mustard in cells Pam212 produce oxidative stress, which can later lead to sensory pain, and that cannabinoid and opioid receptors may have a crosstalk to control pain after nitrogen mustard exposure on mouse keratinocytes Pam212 cells. Moving on to my methodology, we started with the removal of mouse tissue from skin and ears after 6 hours, 24 hours, 48 hours, and 72 hours of application of nitrogen mustard. The doses were 0, 0.3 micromolecules, 1 micromolecule, 3 micromolecule, and 10 micromolecules. Then, RNA was reverse transcribed to cDNA using the very thermal cycle, which consisted of a hot start pre-incubation of 3 minutes at 95 degrees Celsius, 10 minutes at 70 degrees Celsius, and 30 seconds at 55 degrees Celsius. Finally, oxidative stress was measured with the application of an antioxidant called N-acetylcysteine, also known as NAC. For the measure of the full change, we use the threshold cycle. All data is presented as the mean plus minus, and statistical analysis were determined by one-way ANOVA. This led to our results, which in figure 3, it showed that after 48 hours, nitrogen mustard upregulated at 3 and 10 micromolecules. This means that nitrogen mustard act in time and dose-dependent manner. Then, in figure 3a, we used 30 micromolecules of nitrogen mustard and 1 micromolecule of NAC. It downregulated, which meant that oxidative stress was introduced. This will later lead to inflammation and pain. Now, in figure 4, we tested cannabinoid 1 and 2 receptor under nitrogen mustard. After 24 hours at 1 and 10 micromolecules, it upregulated, which means the cannabinoid receptor are involved in the response to pain signaling. Then, in figure 5, we tested opioid receptor delta, kappa, and mu under 30 micromolecules of nitrogen mustard. Only after 48 hours and 24 hours, only opioid receptor delta upregulated, which means that only opioid receptor delta is involved in pain inhibition under nitrogen mustard exposure. To conclude, nitrogen mustard acts in time and dose-dependent manner. As shown in figure 3a, it introduces oxidative stress, which will later lead to inflammation and pain. Then, opioid receptor delta and cannabinoid receptor 1 and 2 upregulated after exposure to nitrogen mustard, which means they may have a crosstalk in sensory pain in mouse keratinocytes Pam212 cells. Taking all together, as shown in figure 6, exposure to nitrogen mustard in Pam212 cells cause oxidative stress, which is responsible for inflammation, and then cause the activation of the cannabinoid signaling in the form of cannabinoid 1 and 2 receptors. Then, opioid receptor delta is activated to inhibit pain. This shows a crosstalk between cannabinoid receptors 1 and 2 and opioid receptor delta to control sensory pain. To finish, for future studies, we want to test nitrogen mustard inducing sensory pain in human skin cells. Further, explain the relation of cannabinoid receptor activation and the downregulation of opioid receptor kappa, as shown in figure 5, and possible pain patterns by targeting neurotransmitter and immune regulators such as chemokines and cytokines. These are my references. Thank you.